Hey everyone, we got Kayla here. Who else is here right now? It is Thursday. It's Haslam Friday. We're on our last Thursday of the semester. I cannot believe it. It is crazy. It's just like, what is going on? How are we almost done with the semester? I know I say that all the time, but it literally just feels like it just started. Can we go over visualization for? Yeah. I watched the last video, but yep, we can do that here. We're gonna start with some what is it, 320? Kayla asked first. And then we're going to talk about some tool one. You got it. Thank you so much, Bailey. I used the code on the slide 100 to build a model from the output. I used the best formula. Which part, Kayla? Slide 100. I do have those open still. Slide 100. Let's go look at slide 100 real quick. Slide 100 says, yeah, this should right here. Oh, it's doing an ordered? Yeah. So, oh, reordering levels. Yeah. So this would work right here. Yeah, although I'd never ask you to do this in class. Yeah. Oh. So, and you're using the best formula output. I never really do this. I never really reorder levels. So that's going in and doing the ordered function. Yeah, to reorder them. It's just the way that they're ordered when you do levels. Here, we'll look at this real quick right here. Then I created a model using, oh, let me go to the, I have the wrong slide version up. Then I created a model using GLM from slide 100 from chapter 7/8. Is this not chapter 7/8? So then I use the best GLM best formula and run the summary, check regression. Which question are you specifically talking about? Good to see you here, Caroline. Which problem are you talking about? Because there's lots of ways to do the problems. There's a lot of ways. I have chapter 6. What? Oh, you're using, oh, are you doing the, oh, nice. Are you doing the model building? I think you're doing model building, which is awesome. Yes, I mentioned it's not required. So this is where it gets really interesting. And I was trying to figure out a way to make it so we could kind of talk about these topics. And so thank you, Kayla, for actually like bringing up these topics, because I was like, well, I don't really want to require everybody, well, back here is space. I don't want to really require everybody to do them, but it's very good to just kind of look at them if people want. And that's really awesome that you're taking a look at these, because this is where it gets really interesting in my book. Like, this is kind of the bridge into data mining, because, and here we'll go to slide 100. And do feel free to download all the slides, because they're great resources. Good to see you here, Roderick. We're going on task 2. There we go. And so let's take a look at this right here. Okay, so what this is doing right here is this is setting the randomness. Let's talk over what's going on right here, making a predictive model. It's setting the randomness. We have right here the train rows are being created. So in predictive modeling, we use a training subset and we use a holdout to see how the model does. So this is literally just creating random rows. This is like in Stat 201 when we talk about taking randomness. This is taking your random sample. And then if you look at this code right here, whatever data frame we put right here, which could be like your EX6 wine data set or your survey 10 or survey 11, that's going to take only the rows from that data set right here. So that takes only the rows, because this is a vector of numbers that we're going to take that are rows and store these rows into the trained data set. So then we're going to put in the holdout everything that is not those rows. So it's the complement of sorts. Like this is the rows, this is not the rows, and it's train.rows. So it won't let me highlight all that right there. And then next right here, we're using the build model function to take a look at the model. And this is actually going to do the all possible models, I believe. So be sure to set your seed. The build model out right here. Then we can take a look at the build model out. So the build model is going to show us all of our possible models right here. So we could actually do that. Do you want to do that one right there, Kayla? Do you want to run the build model on it? It should work for Logistic and everything. Should work. There's a lot of other ways to do it too. If you want to talk a little bit about the whole idea of model building right here, which I do include in number 2, but I don't make it required. So using build model, the output showed, then I don't use. No, that should work. And does that work right there? Is it working when you put that in? When you run all that, Kayla, right there, are you getting a model inside of your GLM, and is it running? And then the GLM should also have, it should also have the family equals binomial. My brain had to like turn on the switch for a moment there. Coffee's settling in. So, I got the project, I got the assignment done last night. I was like, yes. Got the key written. I was like, yes. And then I went to bed. So I was like, I shall sleep now. I shall sleep. Let's go take a look at this. Here we go. And so let's get the data set loaded up. See, good thing I don't grade on like where you put everything, because I'll just put things random spots. I just go right here and go like, there we go, there we go. So I want to clarify that I need to create an actual model. After doing this, I'm confused by the output for the check regression. Oh yeah. We're going to cover the check regression today. So in the check regression, I still have a model stored. Here, let's talk about check regression real quickly here. You ready? So with the check regression, you only get two things. So we have this right here. So here's the check regression. We just talked a little bit about model building, and I'll try to remember in my head that this is the part we're talking about check regression. So this one is kind of iffy. Now, what the check regression is trying to do is it's asking, I can visualize this one. You can't visualize higher order logistic models. It just doesn't have the ability to draw them out. But what are we asking with the check regression? The idea of the check regression is asking if the logistic curve is a what? Like this logistic curve, putting it to the data, if it's a what? We're trying to understand, is it a good this? Like, should we be doing this is kind of the idea. Like, is logistic the right idea right here? That's literally, if you put it out of statistical terms, it's like, should we be really using a logistic model? Like, is this the right idea for what we're doing with this data? Is the sigmoidal curve a good idea? And what do we always start out with? Is it a good fit? Exactly. Is the logistic curve a good fit for the data? Is it the right sort of, like, if you had the idea, if we always talk about like the idea of baking a cake, would the logistic curve be a good fit for baking a cake? I'm stealing my examples from class. So you talk about how long you bake a cake in minutes, and you talk about how awesome the cake is. Like, will people like it? Awesome's too long for me to write. So liking on a scale of probability of people liking the cake, because it's logistic now, not like a numeric like, but will people like the cake with a probability of 0 to 1? Would the logistic curve be a good fit right here? So would the logistic curve be a good fit if we tried to model the probability of people liking a cake with how long we bake the cake? Like if we do minutes from 0 minutes all the way up to, let's say, 500 minutes. How long do you bake a cake for? To bake a cake for 2 hours? So let's go 4 hours. So let's go like, my brain's breaking. Let's go 250 minutes here. So that makes the sweet spot somewhere in here like 120 minutes, somewhere around there. So what would the logistic curve come back and say for this? What would be the p-value for this model right here? And be very careful, I meant p-value for the check regression. What would be the p-value for check regression? Because what it's going to do is it's going to try to fit the logistic curve to this. And it will fit a logistic curve. In truth, it's probably going to fit a logistic curve like that. 120 is kind of high. I don't bake many cakes. Here we'll go 60 minutes. We'll go here 150. It's a big cake. So what would the p-value come back on this? And you might get a model like this because it's going to probably not be, don't worry, that would be actually the model itself. The model itself now is going to have a very high p-value. Like for the p-value for the model is going to be very, very high. Something like this right here. So this is the p-value for the model. The model is going to have a p-value of like this. Probably less than 0.05 for the check regression. And what is the check regression telling us then? Like here, let's differentiate these two p-values. This top one up here is the p-value for the x variable in the model, telling us that the x variable is not very good at explaining whether or not people like the cake. Now you might be like, why is that? Why does time not explain if people like the cake? And Kayla's right, the p-value for the check regression is going to be very low. And why is this? This will help explain why time was not such a good variable, because the p-value for the check regression is telling us what now? Exactly, because it's not a good fit. The p-value for the check regression tells us the sigmoidal curve is not a good fit, and that's why time is probably not coming back as significant, because the model can't use time in a proper way. The model wants to use time that has a monotonic relationship, such that the longer you bake a cake, the higher the probability of people liking it. Like two cakes that differ in their time by 1 minute, the cake that is baked longer has a higher probability of being liked. but we know that that relationship falls off. The true relationship is that there's a right amount of time to bake a cake. Like sometimes you should bake a cake a little bit less. Sometimes you should bake a cake a little bit more. Like people are just saying like, oh, I left it in the oven too long. Oh, I didn't leave it in the oven long enough. There's a right amount of time to bake a cake. Like we could argue what that is within this area, but most people are not going to want cake soup and most people are not going to want a hockey puck. So when you think about what this p-value is telling you in the check regression, it's telling you that this model right here, which is a logistic curve, it's the least significant S-shaped curve. It's a flat S. It's telling you that this logistic curve was a bad idea. Like you should not be using this. So we failed the check regression right here. There was an issue with it. And then this p-value up here is telling you that the information did not significantly change the probabilities. It did not allow us to make better predictions for whether or not someone would like a cake by using the information in minutes. And that's probably due to, and I'm talking about that p-value up there right now, the one I've clicked on. Does that make sense to differentiate these two p-values? Like the p-value for the x variable in the model is this. The p-value for the check regression is this. And the check regression, this down here, is observed right here. Let's show just that output on the screen. And so what is, oh, see, it uses randomness. Oh, I got to remember this for the take home. Oh, I got to remember that for take home. It uses randomness. So you'd actually have to set the seed when you run it. Did I do that on the take home? Set seed 120, why not? Now we'll get the same result every time we run it. So what do you think? We'll only show those results. Now we have conflicting results right here with this. So I think, so what does, and here we'll go to right to Roderick's question. And so this will answer both Caroline and Roderick's question. What does this tell us right here? How would you interpret these results? This would be a harder one. Like if I said, interpret the results of the check regression, and I had you write something, what would you write? Take a moment right now and see if you could, on the test, explain the results of this check regression, which I'm highly thinking of including something like this. So yesterday, if you're in yesterday's class, I talked about this yesterday's class, and I talked about having two friends, how we have two friends who have maybe sometimes have different opinions, which you can kind of see this. So I'd maybe talk about friend one right here, method one. It's just two different statisticians came up with two different methods of running this test to see if the logistic model is a good fit. So you have two different logistic ways of checking the fit of the logistic, of the sigmoidal fit of the logistic model. So many words, so many words. And so the first friend is telling us what? What is the first friend telling us? With my last sip of coffee. No more coffee. What is the first friend telling us? So we know the p-value is high. We know it's not statistically significant. Is that a good or bad thing? I mean, good or bad is arguable, but method one indicates good fit because, but method two, exactly, Kayla, exactly, yep. Method two indicates that we have no worry. The sigmoidal fit is a good idea. Method two indicates that there is some need for some concern. And so I might go ahead and use it because, yeah, exactly. Yep. And Roger, exactly. Great job, Kayla and Roger. Let's throw out some points. I think Mubot's not awake. Oh my God, everyone's going to be mad. Mubot was not awake this whole time. I was not awake. Mubot was not awake. And that's exactly it. So these are the p-values for the check regression. And you always have to remember check regression is a little bit different. Let's throw out 200 because I forgot to wake up Mubot. You also have to remember that check regression is a different idea than p-values for the model. So if we look at the p-value for the model, the p-values for the model are different right here. Everything in the model is statistically significant, which means it's kind of helping out. It's bringing new information to help us explain the probability of somebody being male. So these right here, these p-values are saying that the sigmoidal shape is influenced and they're bringing new information. So that's the p-value up here, which this one is not significant. This one, ours is statistically significant. So it's like if we have, just talk about our example here, we have a line like this and we have an interaction on it. So you're going to have a p-value for the interaction term. So we could just kind of maybe talk about the p-value for the interaction term comes back like something like this. The p-value for the slope comes back something like this. And then the check regression, and I guess we have an interaction and we have a indicator. So you have all these x variables in your model right here. That's also significant. And then the check regression comes back this. So that's the check regression down here. Who's happy with this? Who's not? Are you happy with this? Are you like, no, what does all this mean to you? So this is the interaction term. This is the p-value of the x variable. Sorry, let's put it all. There we go. So hopefully that's labeled and MooBot's awake now. So these are the different p-values we see, and I'll show them in the output here. I understand. Yep, Kayla gets it. So how does this all relate now? And tell me anything else you want to tell us. So is this all good or bad? Is this all good or bad? We're saying here that the interaction is statistically significant. X1 is statistically significant. X2 is statistically significant. So X2 would be an indicator variable. So all of these up here are statistically significant. They're all X's in the model. And that would relate to the following output. Use the model, exactly. So right now, what I'm hovering over, I'll hover over it again. All of this up here is saying that these X's bring with them new information, and that's a good thing. And then we get down to the end of it, where we run the check regression, and it comes back with a p-value that's higher. And the p-value right here for the check regression that is higher is saying use the model. And kind of not, and so be careful with the word good. We're not saying that like they're a good fit or anything like that. I think you're saying they're good that is they bring like new information, they help out, they explain, they're beneficial to our model. They're not, the variation they bring is not likely by random chance. Like we don't want to go too stat wordy, but does that make sense, Roderick? Like X2 is a helpful variable to the model that is not overlapping in the variation that it's bringing. Next, we have to create a table compare all three models. Smaller. So the smaller model here, we'll put a cut in the video because that's good stuff on check regression. I think everyone understands the check regression. Yes, they bring new information to the model. Exactly. That's what this is indicating up here. And then the check regression down here, we're asking, is this whole curve idea a good idea? So this p-value is a totally different idea. I think that's one of the most confusing things about the class is like every time we look at a p-value, we're not saying the same thing. It's a test, and the idea of it being below 0.05 is statistically significant, but it means different things when it is or is not statistically significant. Okay, let's take a look at, what was it? The naive, simple, smaller, and complex. Just to clarify, let's bring up the assignment. So, where's it? There we go. It's all practice. It's all practice. I promise everyone asks a lot of questions, and I really appreciate it. The biggest thing is start early and ask questions. I think Kayla would probably tell people that, like, start early, ask questions. That way, whenever you get stuck, you can just put it up and you can just say, I'll just ask Brian a question. And thank you, Kayla, for starting early. I'm sure a lot of people have used your questions and helps in these videos that you've put out there just to help their knowledge. So thank you, Kayla. Let's throw 100 points out there for Kayla. I really appreciate it because I promise you people are like, yes, I watched the video and then I know the answers. Actually, include the metrics of misclassification rate and condition check. Are these the only things? I think so, right? I couldn't think of anything else. So Kayla is awesome. And so you'll create the table right here from the naive model. So the naive model will be, and funny enough, the other slide we saw actually had it. When you're looking at the naive model, you want to, my brain is breaking. Oh, brain is breaking. When you look at the naive model, oh, you're welcome. That said, everyone, the naive model is the no knowledge model. And so you want to look at the misclassification rate of the naive model. This model would predict everyone is female because the majority here is female. So it would misclassify everyone who's male. The misclassification rate of this model would thus be, I think it's 699. Yeah, it's 699. Just to show you how we get it. It is 699, but just to show. So everyone who is male would be misclassified here. The misclassification rate of the model is 44.778. I would just include that right there. So that's the misclassification of a naive model predicting from this data. The smaller model will be the model you make earlier on. And to get your model's misclassification rates, which you need to do this right here. You need to go to confusion matrix and put your model in. And let's look at my model's misclassification rate. So my model's misclassification rate right here is what we call the off diagonal. Now, what do I mean by off diagonal? Well, when you match up things right here, you have people who are predicted female, people who are actually female, people who are predicted male, people who are actually male. But let's say, I'm actually male, but the model could predict me to be female. It's possible. It's just the way models do. So I might be in this group if Brian is predicted female and Brian is actually male. So I would be in this group right here and I'd be what we call misclassified. This is what we call the accuracy of the model. This is the misclassification of the model because the model was accurate here and the model was misclassifying individuals here or items, whatever it's trying to do, qualities of wine and stuff. So we would take right here and add together what we call the off diagonal. I've already said that a few times today. You didn't know it's called the off diagonal. And so let's go right here and there is, oh wait, oh no. Wait, what's going on? Why has it got 628? Oh, I know why. Okay, you're wondering, you're like, wait, Brian, your model a second ago. Here's why. I used the wrong model. I used a different data set. There you go. So to be correct with the data set I'm using, I was using Survey 11. The naive model for this one is still going to predict, and you can see it over here. The numbers are the same as right here. Hint for the test. The numbers right here are the same as the numbers right here because this is the actual and these are the actual. So make sure you know that. Make sure you know what your output's telling you. Like these are the totals for the actuals. 201. What do we call this display on a contingency table? 201 or 320. This is the what display. Hint, it's on the outside. It's on the edges. It's on there's an M word for it. It's the what display of a contingency table. See if you know that. It's a univariate display. It's the what display of a contingency table. And I can solve the same way over here of doing this. And that is the misclassification rate of the naive, which could be taken right there. And now we need the total again, which is this. And that's the same as this right here. That's 628. And that's the misclassification of the model. Great job, Kayla. Yes, you're remembering everything. That's the marginal display. Marginal displays are univariate displays. So you want to take these values right here to see how the models are doing. And this is a good comparison metric of models to see like, how are my models predicting on data? You know, what is the misclassification rate? You know, how often would your model be wrong when it makes a prediction? Which we don't really have an R squared here anymore, you might notice. The way we are comparing models now is to say which model is better at predicting, which model makes better predictions and just is classifying things correctly more often. I should have put something like that. In lieu of R squared, we will be using, you know, to see how well the model predicts, how well it classifies things. Like, would it be accurate in its classification of a wine as a high quality wine or low quality wine? Yes. What so that should and then you just do a check regression on it. There's no check regression on the naive. You should mention that the naive is not a model. It doesn't use any X's. So you might just put NA right there. So that's a hint on that when I was thinking over that. The slides recommend generalization error. Oh yeah, so if you're using the holdout, which we should totally accept, so you're not required to use a holdout, but that's really, so Kayla, if you want to take this to the next, should we, and then we'll do a 201. So here we go. Let's, you ready, Kayla? Let's take this to the next level right here. You ready? Because we're going to now make a model. This is kind of where, if we had one more week, we would be doing this. If we had one more week, we'd be doing this. Here's the next level. You ready? So let's do this. Okay. So this is the above and beyond, which you're welcome to do. So include check regression results in table of the 3 models. Yeah, definitely see if the model is a good fit because we want to know if like fitting this model was the right idea. And so this is where we're going like above and beyond. So what we want to do right here is we want to create a holdout. Now, if you notice, if you're watching this right now, like in the future, this is not required, but this is like the next step. Well, don't worry. This is hear it a few times right here. Let's take a look at this. You ready? We're going to go here to train.rows. So what I'm coding right now is I'm coding, my brain has to like pause and stop and think for a moment. I am coding something that is going to take 70%. It's just choosing 70 numbers, 70% of the numbers from how many numbers there are in Survey 11. You bet, Amanda. Yep, we're going to do a little of the project and then or the visualization, then we'll do some homework. You bet. So right now, I just chose random numbers. Does this make sense? Choose from the numbers, sample from the numbers 1 through how many rows there are, and take 70% of those, and then store it into train rows. So these are 70% of the row numbers randomly selected. That's what that code did right there. It chose this is what it's sampling from, 1 through the number of rows there are. And it's also sampling 70% of them, so it's taking 70%. And I think it rounds up when it gets a decimal like that. We don't have to worry too much. We could take a look. Did sample 440, 3, 4, 5, 6, 7, 8, 9? Nope, it rounded down. That's all right. So now we're going to go to survey 11 right here, and we're going to take those train rows. So that only takes the rows, and we're going to store this into train. And then we're going to take the same code, but now we're going to make a holdout sample. And there we go right there. So we have, they can do 60%. Yeah, there's literature. Yeah, literature will argue what's the best amount to take. It really is sample size dependent. For smaller data sets, you might want to do closer to like a 50-50. But you want to have enough data to test on. For really large data sets, you can, Dr. Seaver sometimes does 4 holdouts. Because what your holdout's going to be, and so let's talk about theoretically what this holdout is. You're taking, you have a whole bunch of data. Great job, Caroline, too. Awesome work. Like, I like that people are maybe just doing this because they're like, I want to do something new here. We're going to take some of our data and imagine like we bake a pie. And we think we are the best baker in the world. What might we do instead of eating the whole pie ourselves? What might we do? And this might be a bad idea because we didn't randomly sample it. Instead of eating the whole pie ourselves, what might we do to have evidence that we are the best baker in the world? So we're like, I think I'm the best baker in the world. I'm going to bake this pie. Like, there's an apple pie, and we say, you know what? I'm the best baker in the world. No one's better baker than me. So we eat the pie, and we're like, oh, it's such a good pie. Why should I share? Well, we should share because if other people like the pie, then it's good evidence that it's a good pie, right? If you're like, I bake the pie, and I think it's the best, hold a piece for ourselves and give the rest away. Exactly. So this is where we are going to make our model, and we're going to see if it's good, and then we're going to put this over to the side to test later. So this is not going to be part of the process when we make our model. Granny Smiths. Oh, I should make one for Chelsea like that. I should find a recipe and do that. Like, I'll have more free time. If Chelsea came home and I made like a Granny Smith apple pie, I'll put some cinnamon in it because I love cinnamon. I think she likes cinnamon too, but I'm a big fan of cinnamon. But she loves Granny Smith apples. That sounds good to me too. I'm gonna do that, Kayla. Remind me. I'm gonna bake apple pie. So what we have right here is we are going to make a model from the training data. Yeah, is it a recipe? Send me the recipe. Yeah, send me the recipe. And then I'll maybe send, like, I'll post a picture of it or something if I'm able to do it. And hopefully I don't just like fail. So what it is, and I'll show like the process right here. I'll do it in a much simpler sense, and then we'll do a little we'll do some 201 talking about the conditions. I'm gonna make a model, and this is where you'll be like, what, wait? We have, it's XO2 gender. Okay. So I am making a model right now. And this is where your world changes. I gotta look at the take home, make sure it doesn't have. Oh, I made the mistake. There we go. Okay. I made the model on the what data. The model was made on the what data. The model was made on the what data. Brian's model was made on his training data. That's why we call it training data. The model learns from this data. And so now we make the model, and we can see how the model did on the data it was created from. And the model had a misclassification rate for what it was created from. The model had a misclassification rate of the following. But we should be able to put in data. There we go. It's just data, capital data. We should be able to put in holdout here. It should work. Yes, did work. On new data, and actually the model did pretty well. It might did better on new data. Really? If it did better on new data, that's amazing. It usually doesn't do better on new data. It's going to be close. It did a little better on new data. So I want us to think about this for a moment. Everyone here, these 252 individuals, their data was not used to make the model. And if you heard something I said that this was what kind of data to the model? This holdout data was what kind of data to the model. Hint, it's data the model's never seen. It's that 3-letter word we like for information. It doesn't have anything to do with this sort of information, but it's this kind of data to the model. It's a holdout, yep. And so we took this data and we never let the model see it. So these individuals the model had never seen before, right? These are new individuals. Like, we're using this, exactly. So we're using this model to predict on things it's never seen. This model it was not constructed from this data. So if I were to use this model in the real world, like if I were to ask somebody these questions, like how tall are you, how much do you weigh, what percent of time do you think? And here's the interesting thing. Do you think my model would be wrong about 14% of the time or about 13% of the time? What would be your better guess if I used this model in the real world? Like if I take this model that we make and I use it in the real world and I just go around and I see how well it does on data it's never seen before. Yeah, I think we're gonna do that next year. You got it. A lot of people are wondering about visualization 8. That's next on our agenda. Then we're gonna do some homework. You got it. So if we had brand new data, now we wouldn't average them together. Because think about this. If I use it on new data, it's going to be similar to this. This is what it was created from. So it was created from this data and actually was wrong about 14% of the time. And now we wouldn't say it'd be wrong exactly 13% of the time, but probably closer to the new data one. Because the new data was data the model had never seen before. And so when you think about, in a business, if you're going to use a model, you would want to see how it works. You'd want to what your model. Think of a 4-letter word. 13% correct. You'd want to what your model out on new data. Like you'd want to, before you say, let's do a whole campaign based on this model and let's make decisions based on it, you'd want to give it a what. You'd want to give your model a what on data it's never seen to see if it actually works. Kind of like we do in class. You'd want to give it a what on data. You'd be like, let me blank this model right here. Let me see if it actually works. Let me give it a 4-letter word to see how well it does. What would you give it? If you think this word, you're like, oh, this is a test for the model. This is its graduation test. Can you work on new data? Can you predict on things you've never seen? Pretty much a check right there. And not like a check regression, though. This is not checking to see if it's a good idea, like the fit's a good idea, but this is testing it on new data that it's never seen to see how well it predicts. Great job, Reagan, right there. Let's throw some 100 points. So is this making sense why we would use a holdout? So this is a huge thing. If you're taking 474, this is a huge part of 474. Like this is the whole end of the semester. And so this is like its test to be like, should we be using this model? Will it actually work on new data? This is literally the last 2 months of 474. The idea of making models on new data, checking to see if they work, validating them. And you'll see a lot of this if you look at like model building and data mining. You'll see a lot of validation, a lot of checking, a lot of holdout samples, because you have to see that your model works on new data. And so, in the general, I think it might. Let me look. I think it will. There's so many ways to the right answer. Oh, I think it actually, does that compute the misclassification rate for you? I think that does compute the misclassification rate for you, right? And is it, you just put holdout right there? Yeah, look at that. Kayla, 14 point, and look at, Kayla, you are correct. So, there's that. Is that the, I gotta go back. There it is. And it just does the work for you. So Dr. Petrie created this. Sometimes I do stuff the long way. That's the quick way of doing it. So the generalization error gives you the training. Thank Dr. Petrie. Exactly. So it just runs this right here. So, and you could, what's really cool is you can take a look at these functions. If you go to generalization error, should that do it? Yeah. So if you look at what he's doing right here, he's running, this is all the code that runs in the background. Look at that beautiful code. So he runs all of this code right here to give you the answers. Oh my God, let me get smaller. There we go. This is the code that runs in the background when you run all of this. Ah! So we don't have to run all this code. And it's doing k-fold cross-validation here, is it? He's doing k-fold. I guess, oh yeah, he has k-fold false by default. So we can do some k-fold. What? Let me do a k-fold right here. The things you don't know by looking at the code. And then, oh, Dr. Pichu, you're amazing. So you can actually get the validation portion, and this is kind of a good spot to leave it at. This model is an excellent model that I've created right here. The validation's doing all right. The validation, I don't want to I don't want to go into the k-fold cross validation because that'll be another 5-10 or 10 minutes at least. Talk about k-fold cross validation. K just stands for the number of folds. This is k-fold 5 by default. That's what the, if you looked at the function, when you looked at the generalization error, it has 5 by default right here. Oh, and it's doing k-fold repeated. It's doing 5-fold 10 repeats. That's the repeats for the k-fold. Seed sets the randomness. So it's important to understand, like, the more you understand these concepts, when I read this right here, I'm like, okay, it's going to take a model. It's going to, yeah, you got it, Bailey. Let's do that here in 1 minute. You got it. Thank you so much, Bailey. We're going to talk about 3 and 4 conditions. Yeah, let's do those conditions next here. You got it. So is this making sense, Kayla? Is this a good spot to, I think have you finished the whole assignment? I posted it last night, and I think you're pretty much towards the end of it. For those wondering, once again, this is additional stuff. I don't expect people to be doing this. This is kind of like, if we had 1 more week, this would be the end of the assignment right here, doing the the regression, the generalization errors and stuff like this. So if we had a little more time, we would have gotten right here, like 1 more week, we'd be talking about these concepts right here. We do have the misclassification rate though, but then we'd be talking about like misclassifications of holdout versus. You bet. Let's do it. Let's hop over here. We'll put a break in the video. Okay, let's do this. Thank you so much, Reagan and Bailey, for hanging out. I find this stuff, I love statistics. I think people know that about me. I think people know Brian loves stats. It's just so much fun. Let's go look at some data here. Let's do it. You ready? Data time. Okay, it's data time. Let's do this. I've got the actual data open. I've got a sample of 35. Make sure you went to table, and then you go to subset, and you have a subset of 35. Of course, I already have mine. You can go ahead and hit enter, enter. It's probably just going to give us the same random sample, but make sure you have your random sample of 35. That is very, very important for this assignment. I'm not going to really talk about, well, I guess I'm not so concerned about the conditions. So, like, I don't think it's too bad if I basically give away the answers to the conditions right now. So if you're wondering about the conditions, let's just kind of give away those answers to the conditions. And we do have, I think, do I still have this up? Yes, I do. I have all the conditions right here for those wondering. These are something you should definitely write down. These are the conditions we have for all of our tests. And just to make this very, very clear, when you get down to here, this is for means. Oh my gosh, that's not for means. This is for categorical data. This is for means. This is for chi-squared, which is categorical data. Technically, this is chi-squared, and this is means. And 2 means specifically, and chi-squared is 2 categorical variables. So when you're looking at this right here, have this written down. You want to pause when you get to condition 3 and say, what kind of data am I working with? And then you want to pause when you get to condition 4 and say, you know, am I dealing with 2 means, independent means, hint for today? And if we're doing chi-squared, it's count data. Now, there's no real numbers to these conditions, but this is the way I've organized them to keep them straight in my head, so that way I can always do the conditions and get them right. It's like random, 10%, and then you pause, and then if there's 2 variables, you go to a 4th condition. It's not like the world works this way, but works for this class, so we like it. Okay, so let's go ahead and go to Analyze. Fit Y by X. This is going to analyze bivariate data right here. So we have a Y variable of interest, the one we want to understand, and an X variable that's going to do the explaining. So in your problem right here, you're going to go to the gender of an individual is going to explain what their finishing time was, like why they had a certain finishing time. This is the one you want to understand. Why is this happening? Maybe this explains it. So let's go ahead right here and click OK, and we get the following. We do have a bit of an outlier up here. We do have a little bit of a skew, and it's going to be easier to see this if we go right here and go to the red arrow and go to, and this is not required, but I do think it helps, if we go to histograms. This will put histogram borders on it. Not required, but I do think it helps a little bit. I'll probably leave it like that. Yesterday especially, I was moving it around a little bit. So it's however you want it. There we go. So you can see here, this is the one individual up here. Little bit of a left skew to the general, right skew, right to the high, left to the low. Be very careful it doesn't fall down. It's that this is pulled to the right side. We're also going to add in here the quantiles. Let me make it so we can see that again. We're going to add in here the quantiles. So the quantiles will give us box plots on this. It's a little more apparent to see right now. I'm going to unzoom out. It's more apparent to see right here that we do have a bit of a strong outlier, and we do have a little bit of a left skew, right skew. My gosh, right to the high, left to the low, whatever way the tail goes. So we have a little bit of a right skew. Make sure to notice that these are right skew and a high outlier. This one's, other than the outlier, that's not that big of an issue. So last but not least, to make the output, we want to go to t-test. You might say, well, where's the confidence interval? It'll give you one. So we go to t-test, and we have the output right here. There we are. And then we need to change this from 95% confidence. We go here, and we go to set alpha. I am blind. We set alpha to 0.01. Setting alpha to 0.01 will also make a relative 99% confidence interval, because 0.01 and 0.99 are complements. There we go. So we have here a 99% confidence interval. And so with this, we can now talk about our conditions. Well, one, we took a random sample. So this is, if you notice, I clicked away. I don't want that selected. If you have something selected in here, you can click in the white area and it will deselect it. So that's a quick way to unselect data. So we have right here random, condition one. Condition one is met because we randomly selected these. Awesome. Condition two, 10%. I believe the sample size or the population size of this race is something like 590. I might not directly answer this one, but there it is right there. It is 590. And the fact that it's 590 and we took a sample size of 35, I'll let you decide if the 10% condition is met. So think it over. Is this less than 10% of the population? I'll let you figure that one out. Condition three now, we have to go back to our cheat sheet. Make sure to have your cheat sheet. Cheat sheet says we're doing quantitative data. Quantitative data, so we have means. So we need to talk about the nearly normal condition. Nearly normal can be checked by way of large enough. I usually just say nearly normal large enough, but kind of covers both bases. But nearly normal is the condition. We want these to be nearly normal, and we can oftentimes talk about if the sample size is large enough. Now, these aren't that big of sample sizes because we're dividing the 35 over two groups. You could figure out the sample sizes right here. You don't need to include this. But if you were to go here and go to Analyze Gender, you could see that the sample sizes are 15 and 25 respectively. So there were 15 females here, and there's 20 males. So these are not that large of sample sizes. And this is what, and I did email Terry, and he did email back if you saw yesterday's video. And basically, we're looking for your subjective opinion. Truthfully, in statistics, we like to say sometimes things are iffy. Like, everyone's going to say iffy now. Everyone's like, well, it's iffy, because we do see a high outlier for the male distribution, and we do see a, like, this is what you should write. This is kind of a longer one. Like, this is the condition where it's like, I don't know. I'm a little bit concerned on this one because there's a bit of a right skew to the female distribution. There's a bit of a high outlier for the male distribution. Our sample sizes are 15 for female and 20 for male respectively. I do have some concern for, and if you're wondering, you probably select, yeah, you could do this and you could see 20 males down here, and you could do this and you could see the 15 females right there. So there's a lot of ways to find sample size pretty quickly on this by highlighting data and stuff. But I would, this is not where you just say it's met, it's not met. There's not really a quick and easy answer. This is where my Pearson would say it's plausible. Yep, this is visualization number 8. Yep, talking about the conditions right now. If you have more questions, let me know. So I would say like in the words of my Pearson, it is plausible. And please tell me if you don't think the graders are fair. I get the final call on anything. So if the graders ever take out points, I can go back and say they were too harsh, or no, I agree. Like, you should have gone into more detail. We're looking that you understand the condition, and you can look at the histograms right here. It's just that high. Yeah, it depends. It depends. It's like, other than this high outlier for the male distribution, like if you were to pull that outlier in here a little bit, it'd look pretty good. But I mean, I don't know. I'd probably say go ahead and do it, and then we'll just, I don't know. So it really depends. It's iffy. And so now we get to condition 4, which is independent means. Woo, let's go back to an easy condition. Independent means right here means that one mean does not directly influence the other. Changing it to 99% confidence. Yep. Go right here, Kajal. Thank you for swinging by. And go here to set alpha level and change it right there. There you go. So make sure to click those red buttons right there. That will change it to 99% confidence. Thank you for asking. And so now that we're doing independent means, we just need to ask ourselves, does the time for the males, is it directly impacted by the time for females or vice versa? And we can state pretty clearly that male and female times are not directly impacted by each other, and thus they pass the independent means condition. You're welcome, Kajal. Excellent work. So I would say with certainty we pass the independent means. You might be wondering what dependent means are. Dependent means are often like a before and after. It's the quickest way to do a dependence means. Like let's say Brian tests your statistical knowledge at the start of the semester and then tests it at the end, like I give you a stat test. I would hope that it would increase, but your knowledge at the end of the semester would depend on your knowledge at the start of the semester. Like if someone took, sometimes people take AP Stat and they take our course, well then they would have more knowledge coming in, and by the end their knowledge would probably be higher too, but their knowledge at the end would depend on their knowledge at the start. So that would be dependent means. If we did like, let's test your knowledge at the start of the semester and test your knowledge at the end of the semester, your knowledge at the end of the semester would definitely be dependent, not independent, of your knowledge at the start of the semester. So you got two means: people's knowledge at the start, people's knowledge at the end, but they're dependent because knowing someone's knowledge at the start would give you information, or pretty much give a good baseline of what they'd be at the end. So I hope that explains the difference between independent and dependent means. Like if I pick a random female's time, I wouldn't be like, aha, now I know this guy's time over here, which that's 3 or 4 individuals right there, or 5 individuals. Yep, 5 individuals. So knowing a female's time would not give you information about a male's time directly. They're not dependent. One female's time is not dependent on another male's time. Unless you have like couples running, like couples like, they're like, well, let's run this race together. Then you'd have dependent means, like if Brian and Chelsea run a race together and they say, we're going to run this race together, then Brian's time would depend on Chelsea's time. But we have no evidence of that here. So that's when race times would be dependent. If you're wondering, like, when would race times be dependent? If you had like Brian and Chelsea, like a couples race, and you'd be like, well, now the means are dependent. It's because one person's time depends on the other person's time directly if they're going to run it together. So that's dependent means if we were to do it. But we have no evidence of that. I think that, what other questions were there on this? Here's all the output. One thing I think here, I'm going to put a cut. I'm going to call this like mistakes made in the interpretations and stuff. So let's go ahead and talk about this. I'm trying to remember if this is later. So probably the biggest mistakes I see in the interpretation with this output, and here is the output. I've kind of made it all. I'm less concerned about people making output. I'm more concerned with you understanding the output. So I'm not going to directly interpret this, but I want you to notice something. We're doing right here male minus female. So when you think about this, one of these is going to be bigger due to the difference right here. So if we see a negative difference, the second one was the bigger one. And we're talking about how long did it take people on average. That's the median, but it does give some insight into which one's generally higher. And we see one of these is bigger if it's negative, the second one. And if we see a positive difference, then the first one was bigger. So when you get down here to your confidence interval, this is where you have to notice that the confidence interval sometimes, for a lot of people, will go through negative and positive numbers, and it'll also include 0. So by it including 0, that indicates to us that there is not a difference. And this is a small sample size, so we have issues of statistical power, but we have evidence that there is not a difference here. Like, oh my gosh, my brain just broke on that. Don't listen to that. We fail to find evidence of a difference. That's the correct way to talk statistically. We would continue to believe that there is not a difference because 0 is contained in the interval. We don't look for evidence of 0 being the difference. We believe that 0 is the difference until we have evidence it's not. And 0 being inside this interval, because it goes from positive numbers to negative numbers, says that 0 is a plausible value. And also you'll notice over here, we do not reject the null on the two-tailed test. This is the two-tailed test. This is the greater than test. This is the less than test. And the test statistic over here is the standardized difference. This is good stuff for the test right here. On the test, we could easily blank out this value and ask you to find it. So let's go ahead and blank out. You know what? Let's do this. Let's do a little work with this output, because if you're watching this video, I'm hoping you understand all of this output right here and know how these numbers are found. So could you find, let's do some homework. If you have homework questions, let me know. Let's do some homework questions after this. Could you find that? could you find... Oh my gosh, what? I'm going to blank out all the ones I'd want you to find. I'm going to explain how to find them. This is about the extent to which we could remove output. And we could actually find it. Can we do the problem? You bet. Score sanitized test. You got it. Let's do that one next. And so this is all the output we could blank out on you. This is all the output we could remove. One thing we would never remove is we would never remove this. We will never ask you. Now, we could remove other things, but I'm down to the point where, like, I could remove this right here, but I can't remove both of them and then ask you to find certain things. Like, this is, and I could remove, like, this over here and ask you to find certain things. So I could remove that, or I could remove this. But there's a bunch of, like, formulas here that are pertaining to other things. I just want to clarify for the write-up with the conditions and the condition of the role. So I just want to clarify that we should have a write-up with the conditions, and then the confidence interval, and then another short write-up about the hypothesis. Make sure to answer, especially the conditions if they're met, and then go through talking about, like, interpreting the confidence interval, which is kind of what we're going to do here a little bit. But does that make sense, Reagan? I think you're on the right track with that. Make sure the conditions are clearly met. Those are the ones I kind of just gave with the answers for, pretty much, to, like, how to directly answer the conditions. So, and then we're going to look at, like, how to solve. We will never remove this. We will never ask you for that because that's a complicated formula. We won't ever remove that or ask you to solve for that. You're welcome, Reagan. How would you find these p-values right here? How would you find these p-values right here? What do you know about the less than and the greater than? Does anyone know how to find the p-value for this one down here? So if we have a less than and greater than p-value, so we're actually trying to find this green area right here. So we're up, blocking it a little bit. We're trying to find this green area right there, and then how would we find that? So that is the less than. It's the less than our result. This is the t statistic up here. So that's the same drawing, and we have highlighted on it the greater than p-value, and then we want to find the less than p-value. So how would we find the less than p-value? And just think, if I'm shading this whole curve, I've shaded 100% of it. So since I've shaded 100% of it, how would we find this result right here in the output? Well, the less than and the greater than always add up to 1. So we go right here and we just say 1 minus, and we get that right there. So that is the p-value for this one. My brain is breaking. So then you say, well, how about the other p-value? Well, the other p-value is if we take and we merely just, and I wish I could reverse it. I didn't do it correctly today. Had I not? It won't let me change it. If we just reverse this on the other side, and now we're talking about this p-value here, where all we've done is just double this. We know that this is 12.14%, so all we do is take that, times it by 2, and we obtain this. So it's just double the smallest. Double the smallest. So these p-values right here have this relationship that the less than, the greater than add up to 1. And then this p-value right here is double the smallest. It's just a reflection. You can see it up here. And so that's all we're doing right here. Like, you have your less than p-value, your greater than p-value, they add up to 1. And then all you do is... Did that do it? Oh, well, I can't do that today. Oh, don't act weird, Microsoft Word. And so now we have to find the t ratio. The t ratio is the following. It's just the difference divided by the standard error of the difference. And so this is more complicatedly y bar 1 minus y bar 2 over, and just to make this clear, this is y bar 1 minus y bar 2 over, and then the standard error of the difference, which is s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And so we'll write that down here. S sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And so this is all equal to the t. This does not have a star because it is not one related to a confidence interval. So all we do is just take and divide these differences. And this is why it's just a solve for x now. All we're doing is just taking these two numbers right here, negative 29.449 divided by 24.602, and we get negative 1.18, and that's good enough. Let's do 7.1. There we go. Yay. And now you might say, how would we get the lower bound for the confidence interval? Well, when it comes to confidence intervals, and this just goes to everything we've been learning, this is really a good review right here. So when it comes to confidence intervals, you have here the margin of error. The difference is going to be at the center of the interval, and then we would go up to the upper, and we would go down to the lower. So if we know that the difference is at the center and the upper is here, we can solve for the margin of error. So let's go ahead and get the margin of error. And then we will actually add to get the difference because we're subtracting a negative. And that's the distance. So 68.679. Question. Good to see you here, Caroline. And then we will just subtract that to get the lower. So we take 29.449, and then we go negative, and we go minus this. And 98, and here we can show it, 98.1828. There it is. And we solved it. That is the number right there. And that's what we get when we subtract the margin of error. So we were able to solve all of this right here. One of these, I think this one has a slight decimal difference, which is okay. It's just the way they carried decimals in the background. Oh, wait, did I not do those numbers correctly? How did I not? I must have made a typo when I entered those in. Check the tape. So we can go, let's try this again. 29.449, we'll put the negative, divide by 24.602, and there it is right there. Oh, there must have been a typo. Check that when I did it. Because there was a typo, it looks like. No, we hate typos. And it is carrying more decimals, it looks like, in the background, but 1.1970, and then it's just carrying more decimals on these than we have. Like this might have been rounded up or rounded down, but Jump carries more decimals in the background than we do. So we're down to very, very close number accuracy till we get to like the thousands, 10,000s, 100,000s. So it's down to the 100,000s, the same way Jump calculated it, but there's just decimals back here we're not carrying, or it rounded on us. But that does it. That's how we do this output right here, how we interpret it, and how we understand what's going on, that this is a confidence interval for the difference. This is a test right here to standardize the difference, and these are p-values to tell us whether or not we have evidence that there is a difference. The difference is greater than the male, like the males had a higher time, or the males had a lower time on average. And that's got it. Let's take the question right here. Can we do the problem over the homework? The standardized test scores. You got it. Standardized test score problem coming right up. Let's do this. Put on a little music. We need more coffee after this. So much coffee. How many cups of coffee do you drink a day? I drink 2. It's like I sadly look forward to it. I'm like, yes, I get to drink coffee. And then I have an awake chocolate. So that's 2.5 cups. I think one little piece of white chocolate is a half a cup. Half a cup of coffee. It's a great Futurama episode where he drinks coffee. Any TV show where someone drinks coffee is amazing. It's right there. Do you watch Futurama? I collect data on everything. Here we go. The homework. Replace questions. I think it's the 3rd. second. Yep. Let's do this. Turn music up a little bit. Here we go. Let's do the question. Okay, so we got standardized test scores. And this actually relates to the previous problem we were just doing a moment ago, because it wants us to find the margin of error for the interval. So if you look at this interval right here, we have it goes from about 6 to 12. So, you know, if we were to turn this into a much nicer interval, like just ask yourself, what is the margin of error very close to for this? So if anyone's watching right now, which I think we do have some people watching, what is the margin of error very close to for this? What is the margin of error very close to? Just do this. Like when you're thinking about this, don't look at the numbers. Don't look at them. Just call this 6, call this 12, and think about your interval. We'll solve out the exact numbers here in a second. Hey, what's up, Lauren? Good to see you here. If you have any questions, let me know. We're going to finish this question. We can probably do 1 or 2 more after this. What do you think the margin of error is for this interval? What do you think? And we're just rounding it for the moment, but what do you think the margin of error is? It's a rounded version just to make it nice and neat. So when we're solving it, we should be like, you know, I should get something kind of close to this. Like whatever we solve for this and get, we'd be like, you know, should be close to this. So there's the interval. It goes from 6 to 12, rounded version of it. Makes life a little bit easier. And we're like, you know, the margin of error looks to be about plus or minus this on it. Like you would say the center of the interval is 9. That's the very center. You'd say 9 plus this and 9 minus this. That'd be the margin of error. Margin of error is just a little plus or minus on the interval. And right now it looks like 3. So 3 is the margin of error. And it's very close to that. But let's think about how we're getting this. The margin of error is always half the length of the interval. When you look at the interval, the full length of this interval is 6. And 6 divided by 2 is 3. So let's put in our actual numbers here. We need to find those actual numbers now. We're not going to do the rounded version. So all we're going to do is take half the length. There's the real numbers, not the rounded numbers. So the length of this interval is going to be 11.821 minus 5.979. So it's 5.842. That looks like I'm talking about the center. There we go. And then we take half the length. There we go. 2.921. Hey, Lizzie. Which one are we working on? Morgan, everybody. If you have a question, let me know. We'll finish this one off right here. Oh, my gosh. Really? I go 8.9. There's the margin of error. There's the center of the interval. We weren't asked for all this information, but never hurts. 2.921. Right. Is that correct? 2.921. Then I get it wrong. Watch that right there. The margin. So if we had calculated a 90% confidence interval, how would this have changed the interval? So when you think about a 90% confidence interval, a 90% confidence interval is going to be smaller than a 95. And why do we know that? 68, 95, 99.7. 68, 95, 99.7. When you go to wider confidence, the interval is going to get bigger. So it's saying if we had exactly going from a 95 to a 90, it's going to go in. 95, 90, 68, getting smaller. So the margin of error would be smaller because the critical value will decrease. This is it's talking about the t or the z used to make the interval. So classically, 95% confidence with a z are 1.96. 90% would be 1.645. These are t-scores though, but t's and z's are basically the same. And the margin of error would decrease as the critical value, which is talking about this right here, decreases. So it's literally just saying the same thing twice. The margin of error would be smaller because the critical value is smaller, and the margin of error is smaller because the critical value is smaller. It's just repeating itself. Make sure to notice for yours, if you're going to a bigger interval or smaller, we're going from 95 to 90. So we're going down. We're going from 95 to 90. Once again, 95, 90. But if you were to go to 90 to 95, it would be bigger. So just make sure you see which way they're talking about increasing or decreasing confidence. This one has a trick to it. You have to be careful because we're not talking about a student. We're talking about students. So the key right here is we're talking about the mean, and the mean is for students, not a student. A student would be an individual, where this is the difference between all students with non-traditional and traditional. Now, if you notice right here, the interval is positive, and if the interval is positive, hey, Camden, good to see you here. So if the interval is positive, then that means the first number is bigger. What about, I just like chill music. So what about if we had this right here? We want to look on average how many free throws Brian makes versus Darren makes. So we got mean Brian minus mean Darren. And this interval was found to be 20, we take 100 free throws, 20 to 30. So the interval right here is the true difference between how many free throws Brian and Darren make out of 100 is contained in the interval 20 to 30. On average, 20 to 30. What does that mean? And I think this is where people get confused because it's not like Brian makes 20 and Darren makes 30. That's where I think the confusion comes. What we're saying is when we ran this result right here, and we'll put it all over here. There we go. When we did this test right here, do you know what the difference observed was? Who knows from this interval? Ooh, it's a good test question. Can anyone tell me from this interval what difference did we observe when we ran this? What difference? This is what we estimate the difference to be. What was the observed difference between Brian and Darren in the sample, and who made more free throws on average? Like Darren and I have been doing this for years where we each do 100 free throws. That's what we would have to do. Darren and I go out and attempt 100 free throws, and on average, the difference between us is contained in the interval 20 to 30 free throws. So who was better and by how many free throws on average? On average, this person was better by how many free throws? I'm 95% confident the true difference between Brian and Darren's average free throws made out of 100. Brian made more. And I'll show you why. Good. Lauren, 100 points right there. I appreciate it because I'll show you why. Brian made more, and Brian made 25 more on average. Return of Space Pen. Yeah, Space Pen can be hard to read at times. So tell me this. If Brian makes 75 and Darren makes 50 on average, what would be the difference right here? Does everyone see what the difference is? If Brian on average makes 75 and Darren on average makes 50, the difference between Brian and Darren on average would be 25. 25 is the observed difference between the means of Brian and Darren. And then this interval right here is 25 plus or minus 5. So we observe, so Lauren, don't worry. This is, I think a lot of people get confused by this output because it's not like Brian makes 20 and Darren makes 30. I think that's where the confusion is. We're saying like the observed difference between Brian and Darren is somewhere between, post it. I think we got time right after this, Kayla. You got it. Post it. Tell me the question, and then I think we got just enough time. I teach at 1:10. Yeah. What does mu Brian and mu Darren mean then? So mu Brian. So this is like every day Darren and I go out and shoot 100 free throws. On average, Brian makes 75 free throws. So the mu Brian is the mean amount of free throws Brian makes out of 100. Does that make sense? Like Darren and I have been doing this for months right here where I go out and I shoot 100 free throws. That's how I shoot my free throws. I'm great. So I shoot 100 free throws and Darren goes out and he shoots 100 free throws. On average, Brian makes 75. Awesome. On average, Brian makes 75 of his free throws. On average, Darren makes 50 of his free throws. Does that make sense? The difference between how many we make on average was 25, and we estimate that we're 95% confident the true difference between how many we make is between 20 and 30. And this would give you evidence that Brian is better. And look, because the interval is positive, we think the first mean is higher. This was the Brian making up the example. The 20 and 30 was just me saying, let's say the interval goes from 20 to 30. Yeah, so we think the true difference between, and why do you think there is a true difference between Brian and Darren right now? Why would you say this is good evidence that Brian is better than Darren? Sorry, Darren. I used to send him these videos. He'll be like, dude, let's go out and make some free throws. Let's see how good you really are. And I'd be like, nah, that's all right. You win. Why would you say that there's evidence Brian is better than Darren right here? And this kind of goes to the project. Yep, we'll be back later. Which one were you wondering about, Amanda, that we didn't do? We might... Kale might have posted the question to me. If you want to put the one we didn't do, Amanda, in the chat, we can definitely do it. And we will be back later. We'll finish this one off. Why would you say there is evidence of a difference between Brian and Darren right here? Because we're saying we think that the true difference between Brian and Darren, this goes to confidence interpretation for your visualization. Not because, well, 25 is the observed difference. So this is the difference in the sample means right here. So what we actually have right here is what we saw in a sample. This is sample mean Brian and sample mean Darren. So I tried ANOVA with my 2 models. I got 0. Let me take a look at that. Will the partial left not work on it? Yeah, we might have enough time. Here, we'll try to do both right here. So this is what we saw in the sample right here. We saw the difference in the sample, and take a look at this right here. If you look at this interval right here, which of these two teaching methods are better? Because this kind of gets to the last part of this question. Oh, you're right. Yeah. If you want, Kayla, yeah, I think you just found out the issue, which I was like, I haven't seen that issue. Kayla, thank you. You solved your own problem. If you want to just build it on the full data set and do that, which I didn't know it would do that. That's interesting. Do that, build it on the full data set for just an example and be like testing it on the full data set to do the partial F. And it probably, if you build a good model, it should have a low p-value partial F. Great job, Kayla. This one right here, sorry, I got a little sidetracked. We would say that the non-traditional is higher because the interval is positive. So the one that, if the interval is positive, it goes with this number. If the interval is negative, like we go back to our example problem over here, if we had seen... So this is the key right here, Lauren. Does it make sense now that since the interval is negative, who was better? And this is what I'm trying to illustrate with this. Since the interval is negative right now, we saw that Darren made 25 more free throws than I did. Darren has the higher mean. On average, Darren made 25 more free throws more than Brian. We are 95% confident that the true difference between Brian and Darren is somewhere between Darren making 20 to 30 more free throws than Brian, which is probably more accurate to the real world. Darren was better since it's negative. Exactly. And that's what you should immediately notice. So if you're getting that, you're understanding here that when you see this interval right here, the non-traditional had a higher test score because the interval is positive. That's exactly what I want people to see with this. So since this interval is positive, the non-traditional students are scoring on average between this and this higher. And I know it's very easy. You can just like look at what I answer and see this. Yeah, that's what I want you to see. Great job, Lauren. Yes, by understanding what that interval means right there, you're understanding it. And let's take a look. Because the interval does not contain 0, so is there a difference? Because the interval does not contain 0, it's entirely above. There is strong evidence of a difference. And that's kind of what we were getting at with the Brian and Darren interval a moment ago. So I'd use train whole net test, use build model. You can, and then just run a partial, just make a new model and run it and just, does that make sense, Kayla? You can totally do those things right there. I didn't realize on it. And just, does that make sense, Kayla? You can totally do those things right there. I didn't realize that would create that sort of error. But just make a model with the full data set and just say, you could say to test this out to the previous model, I'm using the full data set just to see if it using the full data set. So you could not use the train holdout for your data set. You could just use the EX, like you're saying right there, just use the full data set. And just run it on the full data set. Does that make sense? I hope that makes sense right there. No, we might have time for the one. So like just as a check. If you want to send it to me, I can look it over. But just as like a let's just see if this model does better. Just make one model right there. I think you're almost done, aren't you? On the last steps, amazing work. Yeah. So here let me explain. Okay, so I'm going to put a cut in the video here so that way. Okay, let's go here. I'll get R up. So here, and I'll even take a look at it. Let's go look at some more. Okay. So, which I didn't realize that the partial F got really mad. Yeah, no, it makes sense. You know why? Because when you do the ANOVA, the way it does the degrees of freedom, it's gonna have issues. Make both. Yeah, you'd want to make, so what you have to run to here, this issue, is when you make your model right here, you'd want to switch for the moment and go back to using your full data set just to do a check. Let's call this m.full.check. So this is our full model, our check model. Like we're making a bigger model right here and we're going to check it. So then we could have, like way earlier, a much more simple model. So our simpler model is just, let's call this m.simple. And these are just example models for us to be looking at right here. There's the m.simple. And then this will be the full model. Okay, so we have 3 models right here. Let's talk about what 3 models we have. Cool. Okay. So the 3 models we've created right now, which is more in line for what you're doing here, Kayla. We have the m.simple. We have the m.full. And we have the m.full check. Okay. So I don't know how theoretically I would do this, but like if I would do this in practice, but this is just to talk about like and understand what these things do. So this is just a smaller model using full data. Using all data, I shouldn't call it full. This is larger model using trained data. Larger model using all data. Okay. So with this right here, which of these 2 models, if it works, which of these 2 models should I be able to run the partial F on, which is what Kayla's running into? Which of these 2 models can I run the partial F on? And I hope it works. We'll cross our fingers. So which of these 2 models should I be able to run a partial F on and see if the inclusion of the new variables brings with it new information and predicts the model in a much better way compared to the simple model? And I called it this so I could like check it. That's why I use that name. So I should be able to, theoretically. Yep. Is it mad? Did it do it? Ah, yeah, it did it. And then it's giving the deviance. Let me check one thing. It's not giving the p-value. Do we have to go test equals? Ooh. There we go. You have to go test equals chi-squared. You have to change the test. That is going to be a tricky thing for people to see. It also works that way in the drop 1. So when you do the drop 1 works the same way. It wants the same sort of information. You have to change it to the chi-squared to get it to run and give you the p-value. So there is the p-value for it because we are doing a categorical y, so you actually have to change it to chi-squared. Interestingly enough, overlap between stat 201 and 320. But yeah, is this so you should be able to get this right here. And to replicate the error you're getting, Kayla, if we just do the m.full, it should not like the... There we go. And this is what we're seeing, different size samples used. So that's where it's getting mad if you're using a holdout or using a different size. I didn't know you get that error. That's it makes sense. It's due to the degrees of freedom. Yeah, the distributions would not be the same. So that is interesting. I feel like there would be a way to do it. I'm like searching through my statistical brain, but I see why, because the distributions. In order to run a partial F test, model was used. Yeah, I would totally say that. Yeah. Just to look at the results of a partial F. Since the first one, what you could do, and I'm not saying do this, you could go back and fit it on a training data set. You could, so that theoretically, if we were, like, let's say we were working for a company and we were talking about this, I'd be like, yeah, yeah. And just realize this, tell me if the graders you think are too mean or anything. The whole point of this is to understand the concepts. Like, we're not solving any of the world's problems with this. The whole point of it is to understand, like, when do we use a partial F test? So this is the partial F test right here. This is the drop 1, which is going to drop one variable from the model, and it drops the it does not violate model hierarchy, so it only drops the interaction term and gives us the p-value for the interaction term. So the whole point of this is to understand, what does this output do? What are we doing here by the partial f? Like, and then be able to explain it to someone. If you notice, a lot of this is not just, run the code, get the answer. A lot of this is, run the code and then explain to somebody, why are we doing this? So you want to be like, okay, this partial f shows that the inclusion of the new variables brings with it new information, that it makes our model better. Basically put, we should use the larger model right here. That's what, like, and you do need the chi-squared. Yep. So you need test equals chi-squared to get the p-value. Without it, it won't run the p-value. And so, yeah, does that make sense right here? And so the whole point of this, which I think sometimes drives people nuts in statistics, is like, we're not looking for like a numeric answer. The answer to everything is never like 5. The answer is like, the answer of 5 tells us that blah, 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 blah. Like, it's we're very verbose in our answers in statistics. We want to know why, and like, we literally want to know why. We want to understand and explain, what does that p-value mean right there? Well, for the partial f, it means that we're comparing two models, a simple versus a complex model, and the low p-value gives us evidence that the complex model brings with it new information, and by bringing new information, we're saying it's better. So we should use the complex model. We like the complex model. Let's go with the bigger model instead of the smaller model. It's super statistically significant. Yep. So awesome work right there. Amanda, are you still here? Amanda, are you still here? Let's speed run a question. We're going to speed run a question at the end. You ready? Let's do, we did it yesterday too. We're going to speed run it because I'm going to try to get some coffee between classes. I need my coffee. Coffee. Let's speed run a question. Let's do this. Great job, Kayla. Excellent work. Speed run question time initiated. Here we go. I'm like, do I actually want to speed run? We'll do it just right normal. Okay, let's put on a little music. I love a little bit of music. All right, here we go. Talking over this question right here about cereal and sugar content, because everyone loves sugar. Let's go right here and take the data, copy into a clipboard, and then we're going to hit Control or Command C 3 times. There you go. Command C if you're on a Mac, Control C if you're on a PC. You only need to hit it once. You're going to go into Jump, and when you go into Jump, you want to go to File, and then New Data Table. This can be achieved anywhere in Jump. File, New Data Table, also Control-N or Command-N does it. So we're going to go to the New Data Table here. We're going to full screen it. There we go. Nice and easy to see what we got going on. Now, when you do this, you have to make sure, don't click inside of it anywhere. I know a lot of people do that. You probably already clicked inside of it. You might be all right, but don't click inside of it usually. We're going to go right here to Edit and then Paste with Column Names. You often want to take note if your data has column names or does not. And by column names, I mean these things right here. If you do not paste with column names, you'll get this, and this is an error. Don't do this. So if you have this happen, start over and paste with column names. They will be blue, not red. Start over if you see red right here. Red means categorical. That's not correct. Blue means quantitative. That is correct. So make sure you paste with column names, edit, paste with column names. Once again, up here, edit, paste with column names. Okay, now that we have the data in Jump correctly, we're going to go to Tables, and we're going to go to Stack. Tables, Stack. With Tables and Stack, right here, we're going to double click, and that puts both of them right here. It's going to take both these columns, it's going to stack them on top of each other, so we have one column of data, and then we have another column of the label. So here we are with the column of the label, which tells us the label of the cereal, and the column of data right here. Good to see you, Caroline. And we're going to go to Analyze, Fit Y by X. Now you'll notice this one variable is categorical now, which is going to make 2 groups, i.e. 2 means. And then we have data right here, which is quantitative, so we can analyze the 2 means for the 2 different types of cereal. So that's the goal of this chapter, is to compare 2 independent means. And we're going to click OK. And these are independent means because the sugar content in a random children's cereal does not depend on the sugar content in a random adult cereal. We're going to go here to the red arrow. This is going to give us all the options in Jump. And we're going to go to t-test. This is a 2-sample t-test because we have 2 means, i.e. 2 samples. So now we can see the results. And I think we got that interval. There's the interval. Let's go ahead and put it in. I am 95% confident the true difference between the sugar content of children's and adult cereals is contained in the interval 31.40 or 31. We can't finish it by the end of the song. No. 39.79. So close. We're going to have to repeat the answers right here. We think children's cereal has more sugar content because the interval is positive. Why does it keep doing that? There we go. And that's it. There we go. So those are just the numbers we have. And especially by looking at this, just to make it very, very clear as we end office hours here, get some coffee. So what you're looking at right here is the interval to estimate the true difference between children's and adult cereal sugar content. And you can just see right here, children's cereal has way more sugar in it than adult cereal because children's cereal is awesome. Lucky Charms, you know, they should make a Twix cereal. Oh my gosh, if there was Twix cereal, that'd be my only diet. So we saw a difference of 35.6, which is the difference in the means between the two groups. And we see right here that we're 95% confident that children's cereal has between 31.4 to 39.8 more grams of sugar in it than adult cereal because the interval is positive. And that's got it. We're going to head over here back to space. So we have done some two means today. We've done some chapter. We've done the assignment 11. We'll be back. Let's play a little bit of music right here. I turned the boss. Dramatic music. We'll be back later, everyone. Stay tuned. Great work. Keep up the great work. You're welcome, Lauren. See everyone in class. I guess I got one class here in 13 minutes. Get some coffee. Bye, everyone.